Hello and welcome to the fifth lecture of the Deep Learning course. Today we'll be looking at ways to model sequential data. In the first part, we'll look at the practicalities of learning from sequences. How should we shape our data and what should we expect from our models in order to consume this kind of data? In part two, we'll look at a very popular form of sequential model called a recurrent neural network. In part three, we'll look at a specific instance of a recurrent neural network called an LSTM. In part 4, David will tell us how to use convolutional neural networks effectively to learn from sequential data. And in part 5, we'll look in depth at one of the bigger recurrent neural network models in recent years called ELMO. So what kind of sequential data can we expect? The simplest case is probably numeric one-dimensional sequential data, a time series. In this case, we have a time series consisting of, for every time step, the number of sunspots observed at that moment. We can also have numeric n-dimensional data. For instance, here we have a data set with, at every time step, two numbers, one representing the closing index of the AEX and one representing the closing index of the FTSE 100. Or our data set can be symbolic, where at every time step we are given a symbol from a fixed vocabulary. The prime example of this is probably language, which can be viewed as a symbolic sequence in two ways. We can break it up into words, in which case we have a very large vocabulary, and at each time step we are given one word, as shown above. Or we can view language as a sequence of characters, which gives us a much smaller vocabulary and a much longer sequence. Datasets generally come in one of two types. Either we have a single sequence, or we have a set of sequences. Here we see an example of what a dataset with a set of sequences looks like. This is a very simple spam classification example, where we have a number of instances. Each instance is one email, which consists of a sequence of characters or a sequence of words, and assigned to each of these instances, we have one classification label. The sunspot example we saw earlier is an example of a single sequence dataset, where the dataset as a whole is one sequence, and we can think of the instances in that dataset as the individual observations. And in these kinds of datasets, one very common learning goal is to predict the next token in the sequence given the history. So given these observations, what's the number of sunspots we will observe next? And as you can see, there's a lot of regularity in the data that will help us make a good estimate of what number of sunspots we might observe today. Now, one thing that is especially important when we're dealing with sequential data is to carefully split your data into a training set and a test set, and into a validation set and a test set. The reason is that if we shuffle things along the time dimension, we might end up testing on things that happened before the things we've trained on. And we can sort of, during training, see the future and infer things from the future, which is a benefit and advantage that does not translate to the real world setting. So in general, you want to keep your data ordered in time and split your test and your validation set at a particular point in time, and everything before that point becomes your training data, and everything after that point becomes your test data. And then you do the same thing with your validation set. And if you want to simulate properly the real world case of training up to the moment and then predicting only a very short number of instances after that moment, one good way to do this is to use walk forward validation, where you train on a short training set and then test on a short number of instances just after your training set, and then you move the cutoff threshold to increase your training set, and then again you validate on the time slice just after your training set, and you average all the performance scores that you observe. It's called walk forward validation. So that's the sort of data we might encounter. Sequences consisting of numbers, vectors, or symbols, and our data set might be a sequence per instance or a sequence of instances. So what can we do with these sequences in deep learning? In general, what we do is we build a sequence model on top of this. And the defining property of a sequence model is that it can operate on inputs of different lengths using the same weights. So a single model with the same weights can operate on a sequence of 7 tokens or a sequence of 15 tokens without having to add or remove any weights. For the input, we generally want the sequence data as raw as possible, no pre-processing or anything like that. Deep learning is end-to-end learning, so we don't pre-process the inputs too much. And for the output, any sequence task is basically available. We can do classification, regression, token prediction, and even sequence-to-sequence learning. And the basic building block that we'll be working with this whole lecture is the sequence-to-sequence layer, which we define as follows. A sequence-to-sequence layer is a layer that takes as input a sequence of vectors of length t and produces as output another sequence of vectors, again of length t. And the input and output dimensions may be different, but the length of the sequence is the same in both cases. We can generalize this if we want to from vectors to tensors, but practically for this lecture, we will stick to vectors. And again, the defining property of a sequence-to-sequence layer is that the same layer with the same weights can be applied to sequences of different lengths. So let's look at an example to see what that means. Here's something that isn't a sequence-to-sequence layer, namely a fully connected layer. So here at the bottom, we have our input sequence, a sequence of 5 vectors of 4 elements each. And our output sequence is also a sequence of 5 vectors, and again of dimensionality 4. So far so good. And a fully connected layer between these two is simply a layer that connects every input, every number in the input to every number in the output, which would give us 20 by 20 connections for a total of 400 weights. Why is that not a sequence-to-sequence layer? Because if we now observe an input sequence with, let's say, 6 vectors, then we would need to add some weights in order to apply this layer. By contrast, if we apply a fully connected layer or an MLP to each input individually, then we get a fully connected layer of 4 by 4 connections. If we share these weights at every point in time, then we do get a sequence-to-sequence layer, because now if we observe a sequence of 6 items, we can easily extend the MLP layer with another copy of these 16 shared weights. Of course, this is not a very useful sequence-to-sequence layer by itself, because it doesn't propagate any information across the time dimension. We will see throughout the course 3 types of sequence-to-sequence layers that do propagate information across the time dimension. The first is convolutions. We've already seen these in lecture 3, and we will see them again in a sequential setting in video 4 of this lecture. The second is recurrent neural networks, which we will discuss in videos 2 and 3 of this lecture. And finally, there's self-attention, which we will discuss towards the end of the course in lecture 12. Now, to finish up this video, we'll look at some of the important properties of sequence-to-sequence layers and some of the ways you can apply sequence-to-sequence layers in practical deep learning settings. And this is a bit abstract, so if you want to think of a concrete example, just take a convolution. Just think of a one-dimensional convolution in place of these sequence-to-sequence layers. The first important property that sequence-to-sequence layers may or may not have is causality. A causal layer is a layer that can only look backward in the sequence. So here's an example of a causal layer. Don't worry about the structure too much. The main takeaway here is that when the layer computes the value y3, it can only use x1, x2, and x3 as inputs. And it doesn't have any connections leading from x4, x5, or x6 to y3. And that's called a causal layer. Be careful with that definition. There's also something called a causal model in machine learning and causal learning, which learns instead of the normal correlations that we learn, learns actually whether variables in our data are related through causation. There's not a guarantee that a causal sequence-to-sequence layer will actually do that for you. It's just a name that tells us the layer is wired in a particular way. The counterpoint to a causal layer is a non-causal layer, and a non-causal layer has access to all the inputs of its input sequence to produce any of the outputs of its output sequence. Now, let's look at how to prepare our data so that we can feed it to a sequence-to-sequence layer in a system like PyTorch. First, if our data has discrete inputs, then we need to turn that into a sequence of vectors. One way to do that is by what are called one-hot vectors. So a one-hot vector over a set of options is simply a vector with the same length as the number of options, consisting of all zeros except for one in the place of the option chosen. So here we have a sequence of musical notes, A through G, and to represent one of those notes, we create a vector of 7 zeros, and we make one of its elements 1. So here we've made the fifth element 1 to indicate that we are looking at the note E, and then a simple monophonic piece of music like this can be represented as a sequence of one-hot vectors. Another approach is to create embedding vectors. And here the idea is that for every element in our set of options, every token in our vocabulary, we create a vector of parameters that represents that object. And then to represent a sequence like EDC, we simply concatenate the embedding vector for E with the embedding vector for D and the embedding vector for C, and so on. And like I said, these embedding vectors contain parameters. So all of these numbers on the left here will be learned during the training process of the neural network. Embedding vectors are not specific just to sequence learning. We'll see them in some other settings as well. So let's define the basic principle. If we have a large set of objects, X, and these objects have no features that allow us to learn a representation of them, what we can do is model every object by an embedding vector, where we say that if the embedding vectors for two objects X and Y are similar, then so are the objects X and Y, where similar is some kind of function that we need to define. And then we combine these embedding vectors in some task, like a sequence learning task, and learn the content of the embedding vectors by backpropagation. Now these might seem like very different approaches, one-hot encodings and embeddings, but actually it turns out they're very similar. Because essentially, if your one-hot vector goes into a neural network, at some point, pretty soon, it will be multiplied by a matrix. If you multiply a one-hot vector by a matrix, as you see in this diagram, what you're doing is essentially selecting one column from that matrix. So in this setting, we can basically think of the columns of this matrix as our embedding vectors for the elements represented by the one-hot vectors. And since we very rarely represent the zeros in the one-hot vectors explicitly, we usually use a sparse representation for these one-hot vectors. Practically, it turns out that after implementation, the embedding approach and the one-hot vector approach are very, very similar. In any case, after we've chosen a vector representation for our symbolic sequence, we might end up with something like this, where we essentially concatenate all the vectors into a matrix. So this is beginning to look very similar to the way we normally represent data in a tensor-based system, with one exception, namely that if we look at the set of all instances, they will all have different lengths. And quite often these are vastly different lengths. So in most cases, it's not practical to represent the whole dataset as one tensor. In general, it's more likely that we will keep the dataset as a set of matrices like this, all of which have different horizontal dimensions. And that's not a problem, except for when it comes to batching, when we want to combine multiple instances in one batch. If we want parallelism over the batch dimension, then everything does need to be represented in one tensor. So in order to do that, all the sequences need to have the same length. And in order to give all our sequences the same length, what we do is we pad them. So every sequence is padded with 0 vectors in such a way that all the instances of the batch are the same length. In order to do this efficiently and not to have to pad too much, what we can do is sort our dataset by length. And we will usually get a picture that looks a bit like this, a sort of power law distribution on the lengths of the sequences in our data. So we will see a lot of sequences that are quite short and a rare couple of sequences that are pretty long. And if we do this and then chop our dataset into batches from top to bottom, then we end up with batches of sequences of similar length, which means that we won't have to pad too much. And then to optimize our memory use even more, we can make the batch size variable. So if we're at the start of the data set where our instances are very short, then we can have a very large batch size and still not use very much memory because all the sequences are very short. And as we get to the end, we will have to decrease our batch size to perhaps even just one instance per batch because the sequences are so long. And this allows us to have a more or less constant memory use despite the fact that we have such variety in our sequence length. Another trick that is often used, especially in combination with recurrent neural networks, is packing. Packing starts with a padded batch. And the first step is to annotate that padded batch at the bottom with scanning from left to right how many instances are still left in the batch. So as soon as we start padding an instance, we remove it from the batch and we decrement this counter. So we see here that as soon as the blue instance stops, the counter decrements from 3 to 2. And using this second sequence, we can create what is called a packed batch, which consists of 2 items. First, the data in a single sequence in an interleaved format. So we scan the data column-wise and we skip all the padded cells. And then we add that together with this batch sizes vector. And what this allows us to do is to slide a window over this data vector, which contains all the elements of the sequences that can be processed in parallel. And because we have this batch sizes element, we can shrink this sliding window at any point when one of these sequences disappears. And this allows the sequence-to-sequence layer to move from left to right over all the sequences in parallel, in batched fashion, and simply eliminate one of its copies once one of the sequences has ended. So this is a very efficient way to deal with batches of sequences because we don't actually have to store all the padding in this setting. It is, however, only applicable to models that process the data sequentially from left to right. So you'll usually only see this in the setting of recurrent neural networks. So we have our input data properly batched. We have sequence-to-sequence layers. How can we take these ingredients and build them into model configurations? Well, there are 4 basic ways to do this, depending on what we're trying to achieve. Sequence-to-sequence layers, where both the input and the output of our model is a sequence. Sequence-to-label, where the input is a sequence and the output is a single value, like a classification label or a regression label. Label-to-sequence, where we are given a single value, like a category, and we are generating a sequence to fit that category. And then there's even a combination where we are given both an input sequence and a single label, and our output is a sequence. And that may sound slightly abstract, but we'll look at some examples later. But we'll start with the simplest setting, sequence to sequence. Essentially what we need is an input sequence and we need a target sequence. And then it's very simple. We feed the input to a sequence-to-sequence layer, and if a single sequence-to-sequence layer isn't enough, we can stack a number of them, giving us a kind of sequence of hidden units in between. And eventually we get an output sequence, and we compare the output sequence to our target sequence, which gives us a loss. We sum up the loss over the time dimension, and then we backpropagate. Here's an example, pos tagging. Given a sequence of words, the task is to assign to each word in the sequence its grammatical category, or its part of speech, as it's called. We assume that we have a large data set of, let's say, sentences, together with pos taggings from which we can learn. The first thing we have to do is decide on the size of our vocabulary. How many words are we going to take into account? We map every word to an integer so that our sequence of input words is translated to a sequence of integers. We feed this sequence of integers to an embedding layer, which translates the integers to their corresponding embedding vectors for us. We feed the sequence of embedding vectors to one or more sequence-to-sequence layers, which gives us a sequence of output probabilities. These are raw probabilities, and we can apply a softmax in the vertical direction to turn them into proper probabilities. And these should be probabilities over our output space, so probabilities over the space of all possible pos tags. And then we can simply compute the cross-entropy loss, sum it over the time dimension, and backpropagate. And that will allow us to train a very simple but likely very effective pulse tagging model. One thing to consider is that if we have padded our input sequence, and we will also have padded then our output sequence, we should compute the loss only over the non-padded elements. In some cases, we have a causal model, a model which can only look backward, and we have a more difficult task than something like pulse tagging, a task for which some processing is required. As we read the sequence from left to right, we need to memorize certain elements, we need to combine them together and do some computation on them. In that case, it's often better to make the target sequence start after the input sequence has finished. So here we have a question as our input sequence. You can see that we even leave the model one time step to do some processing before we expect the answer. One particularly interesting thing that we can do with in a sequence-to-sequence setting is what's called autoregressive modeling. And autoregressive modeling is very simple. Imagine that we have a large data set of sequences, which is unlabeled. So all we need is a large data set of, for instance, natural language. Then we can take small subsequences of this and simply set as the target for the sequence-to-sequence model the input sequence shifted one step to the left. So what you see here is essentially that the model is trying to predict the next character in the sequence. And because it's a causal model, it cannot just look ahead in the sequence and return the next character. It has to predict it from the past. And after training this model, assuming we've trained it successfully, what we're essentially building is a probability distribution on the next character in a sequence of characters. And given a successfully trained model like this, we can then do sequential sampling, which looks like this. We start with a small seed sequence of tokens, like characters. We sample our next character from this probability distribution of the next character given this particular sequence of characters, and this is the probability distribution that this network gives us. So we feed it the whole seed, we look at what it predicts for the next character, we sample that from the output distribution, and we append this sampled character to the seed, and then we loop. And this is known as sequential sampling, and the model that we train in this way is known as an autoregressive model. And we'll see some examples of this later when we've looked into how recurrent neural networks work. Now to other model configurations. What if we want to do regression or classification? So sequence to label. A very simple way to achieve this is to do global pooling. So we start with a sequence of inputs, we feed it through several sequence-to-sequence layers, we get an output sequence, and then we simply apply a pooling operation across the time dimension. So either we sum up all the elements in the output sequence, we average them, or we take their maximum element, and that gives us one vector on which we can continue to operate, or which we can take as our class probabilities or our regression answer. Note that this final pooling layer needs to be able to do the same thing on input sequences of variable dimensions, so we cannot just use an MLP there. We have to use something that, like a summing operation, which can be applied to sequences of different lengths. We can also simply assign one of the units of the output sequence as our global unit, the unit that we choose to represent the whole sequence, and just ignore the rest. And then we can feed that through, for instance, a feed-forward neural network to reshape it to the right number of classes. Note that in this case, it's important that if we have a causal model, the global unit needs to be the last unit in the sequence, because that's the only unit that has access to the whole input sequence. Whereas with a non-causal model, we can also take the first token. And note that usually when we have a causal model, it may be that the last token in the sequence has more direct access to the last inputs than to the first inputs. So this may bias the model. So in that sense, the previous approach with the pooling layer is actually more evenly weighted across the input sequence. We may also run into the opposite case, where we are given a label and we want to produce a sequence. The structure here is very simple. We just take this input vector that we are given and we repeat it into a very boring sequence that just repeats the same vector over and over again, and then we feed that to our stack of sequence-to-sequence layers. Now you might ask, what's the use case here? In which case might we see this kind of label to sequence problem? One that we've already seen is the image captioning problem. So we have a convolutional neural network, a 2D convolutional neural network that processes images, results in a feature vector representing that image, and that feature vector can then be fed to a sequence-to-sequence model to produce a sentence that captions the image. And it turns out that if you do this with a bit of transfer learning and a good data set of captioned images, and you train a model like this end-to-end, you already get reasonable captions. However, we can make it one step better by adding also an input sequence. So for this, we need a setting where we can feed both a label and an input sequence to a model. For some models, this can be done natively. If not, what we can do is we can repeat the label into a sequence, and then we can sum or concatenate the label to the sequence and feed that to our sequence-to-sequence network. So this is a slightly abstract setting, but what it allows us to do, for instance, is to combine the label-to-sequence learning with the autoregressive learning. So for instance, in the image captioning task, we can feed the image through the convolutional neural network to get a vector representation of the image, and then feed that to a causal sequence-to-sequence layer together with a shifted version of the target caption. So here, because this is a causal model, it needs to use both information from the image together with the first parts of the caption that it's already seen to complete the caption, as it were. It needs to learn to predict what the end of the caption is going to be. And once we've trained a model like this, based on target captions, we can sample a caption from it by feeding an image through the convolutional neural network, getting a feature vector representation of the image, feeding that to the causal sequence-to-sequence layer, and then sampling sequentially from the sequence-to-sequence layer to generate a caption. And this can really help to make the captions look more natural. We can also apply this principle in settings where we have a sequence-to-sequence task. This is called teacher forcing, and it's often used in machine translation models. So here we have an input, which is an English sentence, and an output, which is a French sentence. And our model consists of two parts, an encoder and a decoder. The encoder is a non-causal sequence-to-sequence model, which reads the input sequence and learns a global representation of it in one vector. That vector is then fed to a causal sequence-to-sequence layer, which learns autoregressively to decode this global representation into a natural-looking natural language sentence. So it's a very complicated model, but these kinds of configurations can be very effective. So, what have we learned? We've looked at sequence-to-sequence models, which are defined by a set of fixed weights that can be applied to variable length inputs. 3 instances are recurrent neural networks, which we're mostly talking about in this lecture, convolutional neural networks, and self-attention. We've looked at several tricks like embeddings, padding, masking, and packing that help us to pre-process our data and to feed it to a deep learning model, and we've seen how versatile these sequence-to-sequence models can be, because we can train sequence-to-sequence, label-to-sequence, sequence-to-label, autoregressively, and we can use teacher forcing, and we'll see more examples of this later in this lecture and later in the course.